there ATS 114 students, Dr. John Troggy, and I'm ready to move on to lab number 7, which is all about cloud droplets and raindrops. This is actually one of my favorite sub-areas within meteorology. This is a part of a discipline known as cloud physics, and cloud physics is all about how droplets grow and fall and break up and freeze and melt, and it's actually a really interesting sub-discipline within the discipline of meteorology, and it's really important because cloud droplets are kind of an amazing thing. The little droplets that form inside of a cloud due to the processes of like condensing water vapor into liquid water droplets or depositing water vapor into ice those little cloud droplets and ice crystals are very, very small. They're about 1,000,000 times smaller in terms of volume than a typical raindrop. In order for these very small droplets of water that are in the cloud to be large enough to fall and fall in the form of precipitation, they need to grow, and they need to grow a lot. I mean, they have to be like 1,000,000 times bigger, and they have to get there pretty fast. I mean, a cloud only lasts a matter of maybe, I don't know, the window of time over which it can form precipitation is maybe only about 15 minutes long. So if the cloud is going to make precipitation, those droplets have to grow, and they have to grow fast. That's a weird phenomenon in nature. I mean, if we had some bacteria that could be 1,000,000 times larger in, say, 15 minutes, that would be astonishing, okay? If babies grew to be 1,000,000 times larger in a matter of minutes, that would be astonishing. But somehow or other, cloud droplets do it all the time. So we have been learning about this business of how cloud droplets grow to form precipitation, and the fact that they grow is actually kind of important and necessary for there ever to be precipitation. Because once you get the droplets fall below the base of the cloud and move into what we call the subcloud layer, that part of the atmosphere between the base of the cloud and the ground, well, they encounter a problem. The subcloud layer is subsaturated. The relative humidity is less than 100% below the base of the cloud, which means the cloud droplets are going to be evaporating. And that is a big problem if the droplet is too small. If the droplet is too small, it will fall, as it's falling through the subcloud layer, it's going to evaporate. You learned an important word about that back in your lectures, virga. Virga is the precipitation that falls but evaporates as it's falling. A droplet that's too small isn't going to make it all the way to the ground. It's going to evaporate because, well, frankly, it's small. It's easy to evaporate. There's just not that much liquid water there, and also, it's falling very slowly. Small, tiny little droplets fall very slowly because they have a very low terminal velocity. Let's make sure we understand that vocabulary word. Any object that's falling through the air has a terminal velocity, the fastest it's going to be able to fall through air. If you have a parachute and you jump out of a plane, the parachute and you have a slower terminal velocity than you have without the parachute. So if you jump out of the plane without the parachute, you plummet at a very high speed and hit the ground. If you jump out of the plane with a parachute, the and parachute system has a much lower terminal velocity, and you'll hit the ground at a very much slower speed. Computing the terminal velocity of an object is a difficult task, but in terms of small little spheres of water that are cloud drops and raindrops, the primary factor that determines the terminal velocity of such a droplet is its size, is its radius. And so for a very small droplet, like a cloud drop, the terminal velocity is very small. I always like to tell students in my lecture that clouds don't float, they fall. When you see a cloud out there, it's falling. The thing is, the terminal velocity of a cloud droplet is like on the order of millimeters per second. It would take weeks for that droplet to fall all the way to the ground, and well, it's just not going to make it. It'll evaporate long before it does that. This tells us something important about the type of precipitation known as drizzle. Drizzle is very, very small. Is made up of very small droplets. They are smaller than like a raindrop, although bigger obviously than a cloud droplet. And drizzle won't be able to fall very far because it's so small. The terminal velocity of a drizzle droplet is just not that big. And the droplets themselves are not that large, so as they are falling, they're evaporating. You're only going to be able to get drizzle to fall out of a fairly low cloud. Now, in the process of learning about how the cloud droplets grew, you learned about 3 main processes that are how cloud droplets grow. The first one was the kind of obvious condensation and deposition. This is the process by which, water vapor in the cloud was condensing into liquid water droplets. You probably remember the word cloud condensation nuclei, for example, the little solids in the cloud, little aerosols that they condensed onto. Or there can be the same kind of process, but it's deposition, where water vapor in the atmosphere is depositing onto ice crystals. But that is converting water vapor into liquid and solid water, and that is one way that the droplet can grow, albeit a rather slow one. You might remember that the challenge here is condensation and deposition converts a large volume of water vapor into liquid water or ice. The problem is it does it in the form of droplets that are just so ridiculously small. They're too small to fall. Now, it's going to be useful to reflect again on this graph we've looked at a couple times both in the course and in the lab, where it's so-called the graph of the Clausius-Clapeyron equation, where it's telling us at different temperatures what is the saturation vapor pressure. Another way to interpret such a diagram is to think about any given spot on that plot as being a combination of vapor pressure, like you could measure it, and temperature. So like the red spot on that diagram there is a temperature of about 27 Celsius and a vapor pressure of about, well, as it happens, about 27 millibars. And that blue dot that's on there is a temperature of about -4 degrees Celsius and a vapor pressure of about 15 millibars, and so on. If you think about it in that sort of way, any spot that you map to on that diagram that is below the curve of the Clausius-Clapeyron equation, any other such spot like the red one there, corresponds to a situation that is subsaturated, and droplets are going to be shrinking because they're evaporating. And any spot that maps above that curve of the Clausius-Clapeyron equation, like that blue one does, is a situation where the air is actually supersaturated, and condensation or deposition will be happening faster than evaporation, and the droplet will grow. Thinking about the graph of the Clausius-Clapeyron equation in that way is actually a powerful tool when we start thinking about the growth of cloud droplets by our second process. You might recall from the lecture, the Bergeron process. Oh, good old Tor Bergeron, one of the great old dead guys of meteorology. Anyway, if we think about this graph of the Clausius-Clapeyron equation, Tor Bergeron discovered a little detail about it. If you actually zoom in on the part of the diagram that's below 0 degrees Celsius, sub-freezing temperatures, and just zoom in on that like I'm trying to illustrate here, you find out that the curve actually splits into two curves. That graph of the Clausius-Clapeyron equation actually splits into two little curves. I'm going to zoom in a little bit closer here. And what you'll see is that there's actually two separate curves. A curve that says relative to water and another curve that says relative to ice. What's going on here? The exact saturation vapor pressure for water vapor depends slightly on what it will be condensing onto. If the water vapor will be condensing onto a drop of liquid water, there's one saturation vapor pressure. And if the water vapor in the atmosphere will be depositing onto an ice crystal, there's a slightly different vapor pressure. That's why you have these those curves are so tiny, the difference is very, very narrow. But the difference is a huge deal because of the situation of what about air parcels that are between those two curves, where their temperature and vapor pressure happens to be between the curves of the Clausius-Clapeyron equation for liquid water versus the curve for ice. And as it happens, most clouds are in that little gap between there, which means by the Bergeron process, the ice crystals, the air around the ice crystal is supersaturated. It has a relative humidity of a little more than 100%, and water vapor deposits onto the ice crystals, and the ice crystals grow. And on the neighborhood around those supercool water droplets, of which there are lots of in a cloud as well, that little area of air around each of those supercool water droplets actually has a relative humidity that is slightly subsaturated. You might have a relative humidity of like 99% or something like that. And as a consequence, those little liquid water droplets, albeit supercooled liquid water droplets, are evaporating. And so what Tor Bergeron discovered was that in a real cloud that is a mixture of supercooled water and ice crystals, the ice crystals are slowly growing and the supercooled water droplets are slowly shrinking. Tor Bergeron thought he had solved the whole mystery of how precipitation happens. He thought this just happened and happened and happened until your ice crystals were big enough to fall. They probably melted as they fell, but that would be it. He didn't have the techniques to get up there into the cloud and actually discovered that this process is neat but much too slow. And finally there was, of course, the process of collision and coalescence. This is the easy one to picture, where two droplets that are both falling very slowly, if they hit each other, they will coalesce into a single droplet that is falling faster. Pretty straightforward, easy to understand what that would be all about. We learned in the lecture that, in general, all three of those processes are necessary to get precipitation to happen in a cloud. And that, in fact, it was necessary to have those three processes happen in a particular order. Okay? But they don't always. Which is why many clouds, most clouds, never produce any precipitation at all. They'll never get droplets big enough that they actually fall to the ground in the form of precipitation. Another detail that's interesting to think about this with regard to collision and coalescence is part of how big the droplet will grow depends on how big of a cloud it's got to work with. If the cloud is a really shallow little layer of cloud, there just isn't that much time for the droplet that's falling to collide with other droplets and coalesce into a bigger droplet. On the other hand, if you have a big thick cloud, your droplet will have had lots of opportunities as it falls to collide with other droplets and coalesce with them and grow into a great big drop. Which kind of gives us another thing to think about with regard to drizzle. Again, drizzle are those really tiny little droplets. Well, how are you going to get tiny little droplets in a big thick cloud? In a big thick cloud, if it's got droplets that are growing, well, they've got lots of opportunity to collide with other droplets as they fall through this big thick cloud. You're not likely to get drizzle out of a big thick cloud. That tells us that drizzle is most likely from very low clouds and particularly from very shallow layers of clouds. Okay. I think you're actually going to have a little bit of fun with this lab. This one's not the hardest lab in the book by any means. Your TAs will be able to help you with any questions that you have, and good luck. Please let me know if you have any questions.